Hello students, we're talking about lesson 3.6, which is proving angle relationships. So similar to our proving segment relationships, there is quite a bit more that goes with angles. So we'll talk through all of that here today. The first thing that they talk about is the protractor postulate. Let's just kind of skip over that for now. You're not going to use it within proofs. So essentially just saying know how to use a protractor. Angle addition postulate. So this is one, and you are going to name it the angle addition postulate. It's very similar to the segment addition postulate, and essentially says that we have a part plus a part equal to a whole relationship. When it comes to angles as well. So the way that it is written is that D is in the interior of angle ABC. Essentially, this is something you can see in your diagram. So you would have a diagram to where you'd have your angle ABC and you'd have D somewhere in the middle of it. And so therefore, you're able to say that like my angle 1 plus my angle 2 is equal to that whole angle that's there. So that's my angle addition postulate. Again, it comes from the diagram there. The next theorem you see here, and for a lot of theorems in this chapter, you are not going to use the names of them. So for instance, I do not allow you to use supplements theorem because most of you will not be able to tell me what that says. So I make you use an if-then statement. And so for this one, you're going to say if a linear pair, then supplementary angles. And what I just did with the abbreviations, you guys are welcome to use. How that one is going to come up as a proof is that if you have a linear pair of angles given, or a lot of times you take it from a diagram to say that you have a linear pair of angles, then you're able to say that they're supplementary. And saying that they're supplementary or that they sum to 180 degrees is the same thing. So you can use either one of those concepts. The complements theorem that you have here, again, you're not going to name it the complements theorem, but the complements theorem allows you to say that if you have two adjacent angles that form a right angle, okay, so essentially if we have a right angle, then the two angles that form it are complementary. Ran out of room over here. Are complementary angles. Okay, that's the idea behind those. Again, an if-then statement is what I'm looking at for there, and I want it to be something that is general and that is true all of the time. Okay, so that's what we'll be looking at with that one. So we're going to use those different statements there. Again, not with the names of those theorems. You're going to see the names used by the book, but we are not going to use them. Okay, so angle addition postulate here. It says, what is the measure of angle 3 if the measure of angle 1 is equal to 23 degrees and the measure of angle ABC is 131? So we have ABC all the way through here, 131 degrees, and measure of angle 3 we know is 23 degrees. And this goes ahead and does kind of a unofficial proof to do this. So it says measure of angle 1 plus measure of angle 2 plus measure of angle 3 equals the measure of angle ABC. So that right there is a form of the angle addition postulate, and so I'm going to throw that in as the reason there. And then they substitute 23 in there, 90 in here, 131 in here. Nice thing is they color code it, so we're going to use some substitution to do that. Again, for those of you wondering like, oh, can we really do that without stating it? Remember, this is not a formal proof. This is an informal proof. So yes, that's okay for what we're doing here. They then add these together. Please know that is not addition property. That is just simply addition. So we have some addition happening right there. And then I'm seeing that they subtract 113 from both sides. So that is subtraction property that says we can subtract it from both sides and still have an equation. And then they took the 113 minus 113, simplified that, and simplified this side. So this is a simplify or combine like terms step there to get to the final answer. So you can justify your work as you go as well, and that's what that one was kind of working on. These two problems right here, I'm just going to throw out there that you guys can do if you want to work on solving. That's not the proof part of it. We've been pretty good about most of that stuff. You know what? Let's go ahead. I will set these up. So if you want to do it first, you can pause the video. Measure of angle 3 if measure of angle 2 is 26. So in this one, I would know that my 90-degree angle plus my 26-degree angle plus whatever the measure of angle 3 comes out to be is equal to 180, because all the way through there is 180 degrees, and we could solve that one. And then over here, 4 and 5, if I'm looking at 4 and 5, those together make 180, so I would do measure of angle 5, which is 2x, plus measure of angle 4, which is x plus 9, is equal to that 180 as well, and solve through that one. Okay, this is where we kind of get into some interesting things, and this diagram in itself is kind of confusing. So a city planner is designing an entrance ramp for a freeway. In the diagram, measure of angle ACD is 45. So they give it to you here as well as here so that you can tell which angle they're talking about. So they're talking about that one there to be 45 degrees. So we've got that angle measure. What is the measure of angle BCA? So we have BCA over here. That's going to be the opposite of that. Now, if I just solve, I'm just doing 180 minus 45, and I'm going to get that it comes out to 135 degrees. So we can do that. But it also says complete the calculations and justify each step. So let's see what they did down here. They said the measure of angle BCA plus the measure of angle ACD is equal to, and we should be able to say in this one, the measure of angle BCD. I'm trying to make sure that I've got all of this. Yes, measure of angle BCD. And this would be the angle addition postulate. So we can fill that in. That's allowing us just to understand that part plus part is equal to whole. And then we're going to do our substitution. So ACD, based on what's given up here, is equal to 45 degrees. And based on the picture, we know that BCD is equal to 180. So I'm going to replace each of those, and I'm going to use substitution. Again, this is not a formal proof, informal proof here. So that's why I don't have to have all of the givens here. And then to go into BCA, then I have to subtract 45 from both sides. So this is just going to say 135 degrees. And to get from that step 2 to the step 3, that is subtraction property that allows me to get to that step. Okay, so that's an idea. Again, informal proof, that's kind of our first time seeing that kind of stuff. Okay, so congruent angles, we've talked about our reflexive, symmetric, and transitive. Again, those come up here, RST 1, 2, 3. We have that with congruence of angles. We also have it with equality of angles. So you're going to see those kind of holding true in here as well. So there's not much new to that. Just know that now reflexive, symmetric, and transitive hold true for congruence of segments, equality of segments, congruence of angles, and equality of angles. Okay, so our next big theorems are here. So congruent supplements theorem, a lot of you will want to use this reason. I do let you use this abbreviation here because it really is an if-then statement, just not written with the if and the then. So we can state this here. But what it says is that angles that are supplementary to the same angle. So make sure you understand this here. It tells us here that angle 1 and angle 2 are supplementary, and that angle 2 and angle 3 are supplementary. So that's what we know from this information. So angles supplementary to the same angle. So angle 1 and angle 3, both supplementary to angle 2. Okay, or supplementary to congruent angles, we'll get into that in a second, are congruent themselves. So angles supplementary to the same angle. So since angle 1 was supplementary to angle 2 and angle 3 was supplementary to angle 2, then angle 1's congruent to angle 3. So again, there's a second little part to this. To the same angle, you could have or congruent angles. That piece doesn't have to be in there. But if that's in there, I could have had an angle 4 over here and known angle 2 and angle 4 were congruent to say angle 1 was still congruent to angle 3. Again, you're not going to call it the congruent supplements theorem. You're going to use an if-then statement or this statement right here. Same thing with congruent complements theorem. We're not going to call it that. We're going to use it. So we're going to say that angles that are complementary to the same angle, again, it could be or congruent angles, but angles that are complementary to the same angle are congruent to each other. So since angle 4 and 5 are complementary, angle 5 and 6 are complementary in this case, then angle 4 is congruent to angle 6 because they're congruent to the same or complementary to the same angle. Last one is vertical angles theorem. Now, the biggest mistake that happens in this is that people tell me that angle 1 is congruent to angle 3 by the definition of vertical angles. So if we have to define vertical angles, the definition of a vertical angle are two angles created by two intersecting lines, and they are the non-adjacent angles. Okay, that's your definition. It doesn't tell you anything about congruence. The vertical angles theorem says that the angles are congruent. So again, I do not allow you to use that name. Essentially, what we're going to say is that if they're vertical angles, then they're congruent. And that's going to be our if then in that case. If you want to say that angle 1 is congruent to angle 3 from the diagram, we can see from the diagram that they're vertical angles, and we can then say that they are congruent to each other. So that's the idea of that one. Again, if you notice there, I don't allow any of those names. We're going to use if then statements or similar statements in each one of those. Okay, so now we get into the examples, and I will talk through a few of the, you could do this or that, and that's where these can get confusing, but I like to give you all the different ideas. for these. So given in this, ABE and DBC are right angles, so they have their given listed right there. We're trying to prove ABD congruent to EBC, so we're going to build to that. So right off the bat, they use the definition of a right angle, which would say that if you have a right angle, then their measures are 90, or if the measures are 90, then they're right angles. So we're going to use that definition here, and you could use an if-then statement if you wanted to. Then they say that angle ABD and DBE are complementary to each other, and same thing with DBE and EBC being complementary to each other here. And essentially that's just going to be, let's just throw this into an if-then statement here. So if right angles, then the two angles that make them up are complementary. So I paused on that one for a second because I always write it different ways, and there's always better ways than others. That's probably not my best rewriting of that theorem, but that was our complements theorem that we saw earlier, so you can go back to that part of the video there. Again, I don't like the names of them because we have to remember what we're trying to say here, and what I was trying to say is if I had right angles, then those two angles that make them up are complementary. This gives an example of where I would allow you to skip step 2 here. So if you're like, why did I state step 2? You really don't need to, because right angles or 90-degree angles are really interchangeable ideas there. And so as long as we state it correctly, then we can skip over that step. So based on my if then, I can skip this step here because I said if I have right angles, which there's my if, then, and I listed what I had. Two angles that make them up are the complementary angles. Okay, so now that I have those listed as complementary, I can now say that angle ABD and angle EBC are congruent because notice that they are complementary to the same angle. And so I'm going to say here that angles that are complementary to the same angle are congruent. Again, if you wanted to put an if then, you can, but essentially you have an if then right there. So there's an example of one of the proofs. Another example, and the best way to learn proofs is to just keep practicing. So I'm going to go through all of these, but here we go. Angle 1 and angle 3 are supplementary, and you can have a paragraph proof, but you definitely don't have to. So in this case, if I was going to do this, angle 1 and angle 3 are supplementary is going to be my given information. And then okay, there we go. Sorry. And then I can go on to my next step here. So I got to figure out what I'm proving. Angle 2 congruent to angle 3. So I'm going to say that angle 1 and angle 2 are a linear pair. And that's going to be based on the definition of a linear pair. So you could say, you can make it an if then. This is kind of a wordy if then, but it's essentially that if two angles are adjacent and form a line in a diagram, then they are a linear pair. That's essentially your definition there. So we can look at a diagram, see that's what they are, and use the definition of a linear pair to state that. And then we're able to state from having a linear pair that measure of angle, hold on, I got to make sure that I'm going to do the right piece here. Linear pair, yeah, we're going to say that angle 1 and angle 2 are supplementary. So there are different ways to do this, but I'm going to go with it kind of what they've done here. So angle 1 and angle 2 are supplementary. I'm doing based on a linear pair. So we know that if there's a linear pair, then they're supplementary. And so I'm going to use that if then statement there. If I keep this kind of moving in that same direction, then I have now stated that angle 1 and angle 3 are supplementary and angle 1 and angle 2 are supplementary. So now I can say that angle 2 is congruent to angle 3 because I have angles that are supplementary to the same angle are congruent. Okay, so that's what you can have there. I started to go into the measures, and you absolutely can, and then do some substitution, but it would be a longer proof in this case, so that's probably the best route to it there. Sometimes long is not bad, just to be clear, but that's kind of our best route there. Okay, looking at vertical angles, let's see what we have here. So angle 1 is congruent to angle 2, and we want to prove angle 3 is congruent to angle 4. So we state our given, then we state angle 1 is congruent to angle 3, angle 2 is congruent to angle 4. So a reminder on statements. Anytime that you look at a statement, you're like, I don't know what the reason is. It can either come from a statement before it. So these don't come from angle 1 congruent to angle 2. That doesn't give us anything there. It can come from the givens. There's no more givens up there. Or it can come from the diagram. Okay, so if I look at this, the diagram, angle 1 and 3 are vertical angles, angle 2 and 4 are vertical angles. Many people will write definition of vertical angles here. That's not right. Okay, what is our if? What do we know? So if the diagram shows vertical angles, so if vertical angles, then we can say that they're congruent. That's my if then there. Okay, now angle 3 congruent to angle 1, you can choose to make that step, but you don't have to. That's symmetric property. What I can do here, though, is I can do some substitutions, and I just have to make sure I get to angle 3 congruent to angle 4 in the end. So let's say that we use these first two steps here. Angle 2 congruent to angle 3. Hold on, let's do that in reverse there, because I want angle 3 congruent to angle 4 without symmetric. So I'm going to say angle 3 is congruent to angle 2 based on these two steps here. And I said substitution, but in this case, we have to write transitive property as to what we're doing since it's congruent. So we have that. And then I'm going to do another transitive property with angle 2 and angle 4 and angle 3 and angle 4 here. So since angle 3 and angle 4 are both congruent to angle 2, they're congruent to each other. And again, that's a transitive property step. So getting used to using those. Okay, another example here. Complete the proof. So angle 4 congruent to angle 7 was given. Angle 5 congruent to angle 4 doesn't come from this. It comes from the diagram there. We have those vertical angles. So again, I'm going to say if vertical, then congruent. So we've got that idea there, 6 and 7 also. We then have angle 5 congruent to angle 7. So I'm going to take a quick peek at this and see, okay, so 5 and 7 both share congruence with angle 4 there. So this allows me to use transitive property in that step there. And then 5 congruent to 6, I believe, is going to be using this 7 and 6, 5 and 7. So 5 and 6 are both congruent to 7, so they're congruent to each other. And that is transitive property as well. So a similar type proof there. Then you get your right angle theorems. So your right angle theorems, things that you can do with this. None of these are, well, most of these are not written in if-then form, but you're going to use these it kind of in if-then form. So I'm going to rewrite them that way. Perpendicular lines intersect to form 4 right angles. This is essentially that if you have perpendicular lines and you can use that symbol, then you have right angles. And again, you can use any of this abbreviation that I'm using. So RT for right, you can use as well. Okay, so you have that. This is also the definition of perpendicular lines that you're going to see, and some of you will use that too. All right angles are congruent. So we will have times that we just need to know we have them saying that they're right angles. So if right angles, then congruent. And we can have that as our statement there, just kind of giving you some brief overviews of these. Perpendicular lines form congruent adjacent angles. So this is an interesting one. The reason you would use this is if you don't want to state both of these theorems together. So if you have perpendicular lines, you can say that you have 4 right angles. And if you have right angles, then you can say that they're congruent. But in this case, you can kind of skip and do that all in one step. There's not really a short way to write that. So that is what you are writing in that case, if you remember that. I would say most of my students just go through the 2 steps on that one. One last memorization there. If 2 angles are congruent and supplementary, then each angle is a right angle. So think about that. If you have 2 angles that are both equal to each other and they sum up to 180, that means they both have to be 90, and so therefore they're both right angles. Again, there's other ways to get through that proof, but there is a shortcut right there, and you can use that if you would like to. There's not really a shortcut in writing that. That's kind of how it goes. Lastly, if 2 congruent angles form a linear pair, then they are right angles. So very similar to the idea, congruent angles, so they're going to have equal measures, form a linear pair. Linear pair we know means supplementary, then they're going to be right angles. You might be thinking those 2 theorems are the same, but sometimes a statement says supplementary, sometimes it says linear pair, and supplementary and linear pair are not always the same thing. So that's why there are 2 different theorems that state those kind of concepts there. Okay. Okay, so some proofs with these right angles. So here we're given angle 1 is congruent to angle 4, so we know that. And we're trying to prove angle 1 and angle 2 are right angles. So angle 1 congruent to angle 4 we're given. Angle 2 congruent to angle 4 doesn't come from that, doesn't come from the given. It comes from the diagram. This is again that if we have vertical angles, then they're congruent. Okay, angle 4 congruent to angle 2, again, something that the book likes to do here with symmetric property. If you want to, you can, but we don't need to there. So we're going to lead this to, I've got to see where we're at here. So this is how you think through proofs. You have to see what they do. If two angles are congruent and supplementary, then each angle is a right angle. So we're going to be able to say we have right angles here, and we need two angles that are congruent and supplementary. So I need to state supplementary here. We've already got the congruence. I'm going to say angle 1 and angle 2. I need to state that angle 1 is congruent to angle 2. I think we have a step missing in here. So angle 1 is congruent to angle 2 by transitive property. That is going to be allowed to be used in there. So we've got our angles that are congruent to each other, but we need two angles congruent and supplementary. So we need to state that they're supplementary here as well. And I would be able to say that angle 1 and angle 2 are supplementary because if there's a linear pair, which I can see in the diagram right there, angle 1 and angle 2, then they're supplementary. That's interesting that those were not in my version of this. There's a chance that some of your books have different typing, so there's a chance that your guys' has that. So then lastly, if two angles are congruent and supplementary, so we said angle 1 is congruent to angle 2, angle 1 is supplementary to angle 2, then each angle is a right angle. So now we can say that angle 1 and angle 2 are right angles. And we're going to just state it exactly as it says right there in the proof statement. Okay. Last one for today. So angle 1 is congruent to angle 4. I'm going to find that in here. That is given. They've written it down there. Lines J and K are perpendicular, so that does make a difference. J and K are perpendicular. Allows me to say that angle 1 is congruent to angle 2. So we can say if we have perpendicular lines, then, and we're going to talk about congruent angles, but then adjacent angles are congruent. It forms congruent adjacent angles there. So we have that idea there with 1 and 2. So trying to jump from perpendicular to congruent without right angles in there, that's the idea of that one. And again, how did I do my if then? You say if whatever you're going from. So it's this information that allows me to make this statement. So from 1 to 2. So the if is the what we're coming from, and the then is what I'm stating here. Okay. Angle 1 congruent to angle 4 is the given, and so therefore we're just using a transitive property to say angle 2 is congruent to angle 4 there. Okay, thanks for staying with me here.